What would happen if all the planets of the solar system aligned? In 1609, famous astronomer Johannes Kepler published the first two of his 3 laws of planetary motion, which held that planets move around the Sun in ellipses, not circles, as they had been widely believed up to that time. He also stated the planets speed up as they approach the Sun and slow down as they move away. Then, in 1619, he produced his 3rd law, which used mathematical principles to relate the time a planet takes to orbit the Sun to the average distance of the planet from the Sun. We know that Kepler was right. Planets in the solar system follow elliptical orbits, where the Sun occupies one of the 2 foci. Kepler's research was slow to gain widespread traction during his lifetime, but it later served as a key influence on the English mathematician Sir Isaac Newton and his law of gravitational force. But how are the planets distributed in space? And how elliptical are their orbits? And what would happen if all the planets suddenly aligned? The solar system consists of the Sun, the 8 official planets, at least 3 dwarf planets, more than 130 satellites of the planets, a large number of small bodies, the comets and asteroids, and the interplanetary medium. The inner solar system contains the Sun, Mercury, Venus, Earth, and Mars. Then there's Jupiter, but between the 2 lies the main asteroid belt. It is a donut-shaped region in the solar system, located roughly between the orbits of the planets Jupiter and Mars. It contains a great many solid, irregularly shaped bodies of many sizes, but much smaller than planets called asteroids or minor planets. The planets of the outer solar system are Jupiter, Saturn, Uranus, and Neptune. Since the first planets were discovered, astronomers noticed their paths were not random, and their orbits lay on a plane that was really close to the orbital plane of the Earth. But how did they define the orbital plane of the Earth? Well, it might seem counterintuitive, but they looked at the Sun. If the Sun's path is observed from the Earth reference frame, it appears to move around the Earth in a path that is tilt with respect to the spin axis at 23.5 degrees. This path is called the ecliptic. Considering the geocentric theory, according to which the Sun and other planets orbit the Earth, the ecliptic is the orbital plane of the Sun. But we know Copernicus destroyed the geocentric theory, claiming that the Earth and all the planets orbit around the Sun. In scientific terms, we say that the geocentric theory was replaced by the heliocentric one. So, it's us orbiting the Sun, and the path of the Sun on the ecliptic is basically the reflection of our path around the star. This tells us that the Earth's spin axis is tilt with respect to the plane of the Earth's solar orbit by 23.5 degrees. Observations during these centuries shown that the other planets also orbit the Sun is essentially the same plane. This is something weird, isn't it? Well, if you think about it, the explanation is quite simple. Most likely, the formation process of the solar system resulted in a disk of material out of which formed the Sun and the planets. This disk had a finite thickness and a finite spread in height, and all the planets formed at various heights in this disk, thus resulting in the orbital planes we still see today. So we know something about the path of the planets in the solar system. But what about the shape of their orbits? The orbits of the planets are ellipses with the Sun at one focus, though all except Mercury are very nearly circular. Classically, the shape of an orbit is defined by means of a math object called the eccentricity, E. The E number is a non-negative real number that uniquely characterizes the shape of a conic section, such as circles, cones, hyperbolas, and parabolas. One can think of the eccentricity as a measure of how much a conic section deviates from being circular. In particular, the eccentricity of a circle is 0, E equals 0, while the eccentricity of an ellipse is greater than 0 but less than 1. So we understand that the closer the eccentricity is to 0, the more circular the orbit. For example, all the planets have an eccentricity less than 0.1, except for Mercury with E equals 0.2. So we have information about the shape of the orbits and the planes where the motion happens. The next thing we want to know is, how big are these orbits? Is there any physical law that describes the scale of the orbits in the solar system? The answer is yes. We have mentioned the third Kepler's law earlier, but what does it really tell us? This beautiful law tells us that a planet's orbital period is proportional to the cube of the length of the semi-major axis of its orbit, and the proportionality constant takes into account the so-called gravitational constant g. If you think about it, this is the physical and mathematical way of saying that the longer it takes for a planet to orbit the Sun, the longer its semi-major axis. So basically, if we know the orbital period of a planet, we can have an estimate of the actual length of its semi-major axis. For example, Mercury orbits the Sun in 88 days, and its semi-major axis is 0.387098 AU long. Instead, Jupiter has an orbital period of 11.862 years, and its semi-major axis measures 5.204 AU. Kepler's third law in action. What we have discussed so far comes from observational evidence. That's why we say Kepler's laws are empirical. What Newton did, among other things, was to give us a theoretical model to describe and predict the universe before observing it. This basically means that given a set of initial conditions called initial state, we could predict the orbit of a planet, a comet, or an asteroid in the solar system. The beauty of Newton's theory is it reproduces observations quite well. Then, of course, Einstein's general relativity theory improved the accuracy of the model. But for the sake of this video, we want to make use of Newton's predictions to see what would happen if all the planets suddenly aligned. First of all, we must say that given the tilt of their orbits and their orientation, the 8 major planets of the solar system can never come into perfect alignment. The last time they appeared even in the same part of the sky was over 1,000 years ago in the year 949, and they won't manage it again until May 6, 2492. This is what predictions based on physics say. But let's suppose a configuration like that was possible. What would happen in that case? Are you still here watching? We constantly strive to make videos that excite a curious person like you. So be sure to subscribe now and press the bell notification. Even if the planets did all align in a perfectly straight line, it would have negligible effects on the Earth. Fictional and pseudoscience authors like to claim that a planetary alignment would mean that all of the gravitational fields of the planets add together to make something massive that interferes with life on Earth. In truth, the gravitational pulls of the planets on the Earth are so weak that they have no significant effect on Earth's life. There are only 2 solar system objects with enough gravity to significantly affect the Earth: the Moon and the Sun. The Sun's gravity is strong because the Sun is so massive. The Moon's gravitational effect on the Earth is strong because the Moon is so close. The Sun's gravity causes the Earth's yearly orbit, and therefore combined with the Earth's tilt, causes the seasons. The Moon's gravity is primarily responsible for the daily ocean tides. The near alignment of the Sun and the Moon do affect the Earth because their gravitational fields are so strong. This partial alignment occurs every full moon and new moon, and it leads to extra strong tides called spring tides. The word spring here refers to the fact that the water seems to leap up the shore with extra strong tides every 2 weeks, and not that they occur only in the spring season. Let's give some numbers. Using Newton's law of universal gravitation, we can, for instance, calculate the gravitational force that a 100-kilogram person feels from each astronomical body when he is located on Earth's surface as the equator. The Earth itself gives a contribution of 980 newtons. The Sun gives something like 0.60 newtons, while the Moon accounts for 0.004 newtons at the closest approach. All other planets give an average contribution at least 2 orders of magnitude lower than the Moon. For example, in the case of Jupiter, the most massive planet, we find 0.000037 newtons. On May 6, 2492, the planet will be in the same 180-degree wide patch of the sky as you can see here. This image shows what you would see if you were off the coast of New York City, and you look due south at 5:10 a.m. on May 6, 2492, as calculated by the software program Stellarium. So we will never see this huge alignment happening. What we can observe, however, is the conjunction of 2 or more astronomical objects in the sky. For instance, Mars and Uranus will be seen really close to each other on August 1, 2022. They will both be in the constellation Aries. The pair will be too widely separated to fit within the field of view of a telescope, but will be visible through a pair of binoculars. Why don't you get yours and take a look? Then, on December 29, 2022, right before the end of the year, you might be able to observe the Venus and Mercury conjunction. The astrology community strongly believes conjunctions have some effect on humans' life. This, however, couldn't be further from the truth. Conjunctions are just random alignments of the planets as seen from our privileged position on Earth. If you happen to be on another planet on the same day, you wouldn't be able to spot any conjunction at all. Better said, you might be able to see some, but they would be different from the ones you would observe from Earth. This is just to remind you that, most of the time, it's all a matter of perspective. That's all for this video. What did you think about the video? Let us know in the comments below, and be sure to watch our other video about the solar system through YouTube end screens and playlists.